Before I start with quantum chemistry, I would like to introduce my YouTube channel, which I opened on last November. The title of this YouTube channel is Basic Physical Chem in English. In Korean, 수포자가 배우는 물리화학. If I translate it into English directly, it is Physical Chemistry for Math and Logic. Uh, Here I explain a very small concept of physical chemistry within 1 minute. So within a short movie, uh, a very small concept of physical chemistry is explained. So my idea was that if you watch one short a day, probably it will take only several minutes for you. And after several months, if you do that every day, after several months, you get more used to physical chemistry, a sub-discipline of physical chemistry, for example, quantum mechanics or quantum chemistry. So far, I uploaded about 90 shorts about quantum mechanics or quantum chemistry in Korean, okay, and then also about 90 shorts about quantum mechanics in English as well. So of course, I can actually make the quantum mechanics content broader and broader, but I try to explain the basic concept of quantum mechanics, which are sufficient to go further to spectroscopy and also statistical thermodynamics. So after uploading about 90 shorts uh, about quantum mechanics in Korean as well as in English, I stopped with quantum mechanics, and several days ago I started with spectroscopy. Content of the first 5 to 7 weeks probably of this class, Advanced Physical Chemistry 1, can be found actually in my YouTube channel. So you go to the this YouTube channel and watch several shorts, and then probably you can determine whether this class, the level of this class, would be appropriate for you or not. Probably it could be too difficult, it could be too easy, I don't know. All right, so let's start with quantum mechanics first. Duality of matter, particle and wave. You have heard about this in general physics or general chemistry, right? And that is actually where the quantum mechanics start. Quantum mechanics starts, in my opinion. So all matter in the universe behaves both as particles and waves. So you generally may have heard about the duality of light. Light behaves like particle on one hand and also a wave on the other hand. But it is not only for light, but also for uh, every other matter in the universe that this duality is valid. To be more precise, the motion of every particle exhibits wave-like properties. On the left side of the equation, so you can find here an equation which is called de Broglie equation. I think this is one of the most important equations in chemistry. You may have heard about this de Broglie equation already in general chemistry. I'm also teaching general chemistry for the freshmen of uh, the university in the natural science college and also engineering college. And we teach de Broglie equation already in general chemistry. You may have heard about it. According to the de Broglie equation, the mass multiplied by velocity. What is this? Mass multiplied by velocity. This is momentum, right? And this is momentum. We generally uh, note this momentum in general physics, in macroscopic classical physics with p, right? Small p. So mv, according to the Bohr equation, equals to h over lambda. So lambda is wavelength. Okay, how much a periodic wave propagate, okay, in length in 1 unit. Okay, the length of 1 unit of the wave, that is wavelength. And then h, that is a Planck constant. On the left side of this equation, we see particle-like properties. You have something which has mass, and also it moves with a certain velocity. That is a very typical feature for a particle, okay, an electron, an atom, a molecule, okay, a rock, probably. They can have masses and also move with velocities. And these are all particles, discrete particles, right? Uh, when multiplied, they give momentum, as I told you already. Mass multiplied by velocity is momentum of a particle. So this is basically describing one-dimensional motion. Okay, one-dimensional motion. Particle moves, so with a certain velocity along a certain axis. Okay, and it has a certain mass m. On the right side, we have wavelength, a property of wave. As I already mentioned, well, wavelength is the length of a unit of wave, and that is a property of wave. So you can see within an equation, the Bohr equation, on the left side you can find particle-like properties, and on the right side you can find wave-like properties. So a matter is particle and a wave at the same time. This is what the Bohr equation is showing us. Okay, that is actually the basis of the quantum mechanics. Electrons, nuclei, molecules, soccer balls, even rocks, all of them are particles. So yet their motion can be described as wave. Okay, this is what this De Broglie equation is telling you. So they are all particles. So all these matters, even here, electrons, nuclei, molecules, soccer balls, rocks, they are all particles, but their motion can be described as waves because according to this equation, when the momentum of the particle is defined, then wavelength can be defined as well. So when a particle-like property momentum is defined, then the wave-like property lambda wavelength can be defined as well. So a matter should be particle and also wave at the same time. More strictly speaking, a motional particle should be also wave-like feature at the same time. So because of this wave nature, energy becomes quantized. So quantized energy levels means that energy levels are discrete, not continuous, but energy levels are discrete. Why energy levels are discrete? Because of this wave-like nature of matter. Quantization exists, well, everywhere in our daily lives. We just don't notice it. We generally think that quantum mechanics is a theory only valid for very small systems, but that is not true. Quantum mechanics can be also extended to the microscopic world, well, our daily lives. But actually, when the scale becomes larger and larger, we don't see that because the discreteness becomes smaller and smaller, unnoticeable. So the energy gap between adjacent energy levels becomes smaller and smaller as the scale of the system becomes larger and larger. So in our daily lives, in the classical macroscopic system, we don't notice energy gap because they are very small. Energy gaps are very small, so that the energy levels look as if they would be continuous, even though they are not really continuous but discrete. And when the system becomes smaller and smaller, the energy gap between quantum levels become larger and larger. And then the quantum mechanics, the quantum mechanical properties become more and more pronounced as the system becomes smaller and smaller. Okay. So if someone claims they fully understand what it means for a particle to be a wave, they are probably lying. It's not something you logically comprehend, you simply accept it. The wave nature of particle motion, where quantum mechanics begins. So, I mean, we are not really very used to describing the particle wave like duality because our language, our logic is based on what we are seeing, what we are undergoing, what we are experiencing. And we don't really experience the duality of matter because this is something which becomes more and more pronounced as the system becomes smaller and smaller in the scale of atom and molecule, but we don't see that. So our logic, our language are not really that appropriate for describing those which we do not actually undergo experience in our daily lives. So probably if you feel you logically really uh, understand these quantum mechanics, I would say probably you're an alien or probably genius. So if you do not understand the quantum mechanics, it is very, very okay, I would say. Right. Wave and energy quantization. Imagine a string. So here you can see a string, okay, the rubber string, okay. The rubber string, imagine a string stretched along the x-axis. You have a rubber string, you have a rubber string here, okay, like this, and the string is stretched along x-axis, as you can see in this figure. Right? The position of 0 for x-axis, okay, here the x value is 0, okay, and here the x value is L, so this is x-axis, right? So now you assume that at both ends with a coordinate of x of 0 and a coordinate value of 0 and L, the ends are fixed. So if you have a string, then you just grab both ends of the string very strongly, okay, and the position at you 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 hold the string is actually 0 and L for the x values, and the end are fixed, so the string cannot move here. So here you hold the string, the rubber string, very strongly, so that the rubber string cannot move actually at these positions. And then if someone shakes the string at this situation, so if someone shakes the string, so if someone grabs this string, rubber string, and then moves up and down, okay, then what is going to happen is that, I mean, there will be some periodic wave appearing within this system. Now, here and here, the position of the string will be held uh, fixed, and only the the string here in the middle will move up and down, okay, fluctuate, oscillate. So if someone shakes the string, okay, under these circumstances, only certain standing waves, like the red one and blue one, can form. That means that for the red one, you can see the half of the wavelength. Half of the wavelength is the same as the length of this end where the positions are fixed. Okay, this is for the red one. Okay, this is for the red one. And then for the blue one, the wavelength is L. So only those waves with certain wavelengths can actually appear within this system, because the string at the position of x equals 0 and L is actually fixed here in position. These waves appear only when the string length fits an integer number of half wavelengths. So when n would be integer, n would be 1, 2, 3, 4, something like that, integer, then only when the half wavelength multiplied by n would be L, the waves satisfying this condition would appear actually within the system, otherwise not. So the ends are fixed, so not every waveform is allowed. So the ends are fixed, and this is something we call in quantum mechanics boundary condition, right? So what I'm actually here trying to more classically explain is the situation for having the infinite potential at the position of x equals 0 and x equals L. So think of the de Broglie equation we learned already in the previous page. The de Broglie equation we learned here. This is de Broglie equation. So think of the de Broglie equation. If only certain wavelengths are allowed, then only certain momenta are allowed. Okay, and if momentum is quantized, then energy must be quantized too. You know that the kinetic energy is p square divided by 2m, which is a half mv square, right? So when you have only certain wavelengths, then only certain momentum values are allowed according to the momenta are allowed according to the de Broglie equation, and then ultimately only certain kinetic energy values are allowed. And this is why energy levels are discrete. So this is, well, I think the most fundamental and easy explanation about why energy becomes quantized, why the energy levels are discrete. Number one, because matter is particle and also at the same time wave, because of the wave-like nature. And second, because of the boundary condition, the end of the string phase. Okay. So because of this, the energy levels can become quantized, because only certain lambda values can be allowed in that system, and then only certain momenta are allowed. Ultimately, only certain kinetic energies are allowed. Well, waves and their energies in a confined space. So same picture here. So you have the x-axis, you have x-axis, okay, you have x-axis, and then at the position of x equals 0 and x equals L, the string is fixed. On both ends, the string is fixed, and you can move only uh, the position of the string between x equals 0 and L. And then, well, the wave with the longest wavelength you can think about in this system is this one, where the half wavelength is the same as the length of the system, L. Okay, half wavelength is the same as L. Now, in this situation, the wavelength itself is the same as L. Okay, and then here 3 times half wavelength, 3 times half of the wavelength becomes the same as L. Here, half lambda is L, here lambda is L. So as you move from bottom to up here, among these 3 different waves, the wavelength becomes shorter. Okay. At x equals 0 and x equals L, the wavelength height is zero due to fixed boundary conditions. We have already discussed about that many times in the two previous slide. In the previous slide, uh, among all the possible standing waves that can exist inside this region, only three of the lowest energies are shown here. Okay, along with their corresponding wave functions. So these are now described mathematically like that. Probably I'm going to show you, uh, explain you also about the sine and cosine function, sinus and cosinus functions later on. But probably I think you may have already learned about this sine cosine functions. I think in the high school. So well, this mathematical description corresponds to this wave. Well, this wave function corresponds to this wave. This wave function corresponds to this wave. Uh, along their corresponding wave functions, as you can see here. Okay. So, strictly speaking, each wave is proportional to this wave function. Okay. Not exactly the same as this wave function given on the slide. If we think in terms of the de Broglie relation, the shorter wavelength, the greater momentum becomes, and consequently the kinetic energy also increases. So according to the Broglie equation, P equals lambda over h. When lambda becomes shorter, then momentum becomes higher, and ultimately also kinetic energy becomes higher. So for moving from bottom to up, wavelength becomes shorter, and energy becomes higher, right? This corresponds to the following situation. A particle with a certain mass trapped in a potential well, the walls at x equals 0 and x equals L are infinitely high, and the particle moves freely between them. A particle with a long wavelength moves slowly, while a particle with a short wavelength moves fast. So this is the wave model I showed you. So what is the corresponding particle model for particle? This situation can be described like this. You have a kind of potential box here. Here x equals 0 and x equals L. And at the boundary, at the position of x equals 0 and x equals L, the potential energy is infinite. The potential energy is infinite. Okay. So at this position, there can be no kinetic energy. Now, a particle can move within this potential box freely because when x is smaller than L and larger than 0, potential energy is 0 and only kinetic energy exists. Okay, so infinite potential at x equals 0 and x equals L, a particle can move one-dimensionally only between x 0 and L. Okay, and inside this potential well, there is no kinetic and there is no potential energy, so only kinetic energy exists. So basically, a particle can move freely. This is a particle-like feature corresponding to this wave model. So the infinite potential well for a particle actually correspond to the situation that at that position, the spring is hold very strongly so that the spring cannot move. As the potential becomes lower, the force that you are holding the string becomes smaller and smaller. So you are holding the string um, more loosely and loosely. Okay, as the potential energy in the particle picture becomes lower and lower. So anyhow, then in a wave picture, you have a long wavelength wave. This corresponds to a slower moving particle. You have a wave with a wavelength of shorter wavelength, and this means a more fastly moving particle. So what does the wave function mean? What does a wave function mean? The square of the wave function. Uh, the wave function doesn't exist. Uh, the wave function itself is actually something that you cannot observe, but the scale of the wave function is something which is physically meaningful. Uh, so before observation, a particle actually doesn't exist as a particle, but only as a probability. That probability is described by the scale of the wave function. First, we introduced the wave function, but the scale of the wave function represents a probability. Strictly speaking, since the wave function is complex, the probability density is the product of the wave function and its complex conjugate. So about the complex, so in number we have the real number and imaginary number. When a number is described by by a combination of a real number and an imaginary number, it is called a complex. We are going to discuss about that also later more in detail. Probably you may have already heard about imaginary numbers. You learned about them in high school mathematics or middle school mathematics probably. I'm going to show you why you have to learn imaginary numbers in quantum physics. It is really essential to know quantum imaginary numbers to understand quantum mechanics, quantum chemistry. So, before observation, a particle exists as a probability distribution. So this is also something which is in a very tight, in a connection, very strong connection with the Heisenberg's uncertainty principle, which I'm going to also show you later, explain you later more in detail. Before observation, a particle exists as a probability distribution. When an observation is made, the particle appears at a specific position. If we repeat the measurement many times for particles with the same energy, their positions follow this probability distribution. That distribution is the scale of the wave function. Actually, we already learned about the scale of the wave function, the probability distribution in general chemistry, which is orbital. Right? Orbital is basically the probability distribution of an electron before observation at a certain energy level. Okay. Uh, so as you can see here in this figure, you have two different waves here. In this case, so I have to probably mention once again that the integer means that you multiply integer to half of the wavelength, it becomes L. So when the integer becomes larger and larger, the wavelength becomes shorter and shorter, and energy becomes larger and larger. Right? So when n is 1, the half wavelength is the same as L here. Uh, the wavelength is the longest, and in terms of the particle motion, the particle moves the slowest here in this situation. And in the case that n is 8, then the corresponding particle moves faster. Now, the wave functions are described here, and here the respective scale of the wave functions are described here. This is the scale of the wave function for n equals 8, and here you have the scale of the wave function for the situation of n being 1. So, uh, when you look at the scale of the wave function of n equals 1, then you can find this kind of distribution. That means that there is almost zero probability to find the particle at both terminal places of the box, okay? And in the middle of the box, you have the maximum probability to find the particle. Well, more precisely speaking, the highest probability in the middle of the box to find the slowest moving particle, okay? Before the particle is observed, the particle exists only as a probability, And then at the the time being of observation, the position is determined. And if you repeat observing, well, the particle with the same energy in the same box many, many times, and you can find that probability distribution. Does that mean particles exist only as probability until they are observed? Yes, that is exactly what quantum mechanics says. If this feels uncomfortable, that's very normal. If it feels obvious, you might be an alien. So I think many things which are described in quantum mechanics, if you understand them very smoothly, I would say that would be abnormal. I mean, the normal human being would feel very uncomfortable about uh, the quantum mechanics. So I told you that this is not something you really clearly comprehend, but this is something that you have to accept. Okay, so along this probability story, let me give you one more example, which might sound actually very weird. Before observation, half and half. At the moment of observation, 0 to 1. So let's say there is a 50% of the probability that a male exists inside the box. And at the same time, also, there would be 50% of the probability that a female would exist inside a box. So inside a box, there are two people. The probability that a person inside the box is male is 50%, and the probability that the person is female is also 50%. Both people are in a state of half male, half female. Okay, so it doesn't mean that one people, one is male and the other one is male. But before observation, one person is 50% male and 50% female, and the other person is also 50% male and 50% female. One person leaves the box and is exposed to others, so to surroundings, to environment. The person is observed as male. So this 50-50 guy moves out from the box, and an observer observes this guy to be male. Since one person has become male, in other, in order to preserve the 50-50 probability, the person remaining inside the box becomes female. Okay. Before observation, the states are not determined the moment someone checks the state of one person. The moment of observation, the state of the other person is simultaneously determined. Observation causes a state collapse. Okay, what is going on is the following thing. Okay, this guy turns out to be a male. And then you have to preserve this 50-50 probability. Okay, and now the person the inside the box becomes female in order to preserve 50-50 probability. Now this turns to male, and now this should become then female to keep this 50-50 probability. Okay, at the observation, the stage of both are determined. Okay, so this is called observation causes state collapse. The key point is that it is not the object itself, but the act of observation that defines reality. This sounds crazy, right? I mean, this is something very similar to Schrödinger's cat, right? Schrödinger's cat, you may have heard about it. So this is a metaphorical explanation of quantum superposition, a fundamental concept in quantum science, including quantum computing. So in one dimension, a wave trapped in a box can only have discrete energies labeled by integers, well, nx, 1, 2, 3, 4, 5, and so on and so forth. The energy is proportional to the square of this integer. So every time the quantum number increases, the energy jumps a lot. But But we don't live in a one-dimensional world. So far, I explained everything based on the one-dimensional system. The particle is moving only along one single axis. The wave is actually lying on one single axis. Okay, but actually, we live in three dimensions. So inside the three-dimensional box, waves can oscillate along x, y, z axis. So basically, you have to think that this is not single string, but actually you have a well, a kind of entity, and fluctuation is made actually along x, y, z axis, along all three different axes. Well, that means we need three quantum numbers: nx, ny, and z. Kinetic energy depends on nx squared plus ny squared plus nz squared. Uh, these three integer numbers are called quantum numbers. Sounds familiar? But remember atomic orbitals. We learned about atomic orbitals in general chemistry, right? An orbital is described by principal quantum number n, angular momentum quantum number L, and magnetic quantum number ML. Well, of course, I mean there is a fourth one, which is spin quantum number, but I mean, we are going to discuss about this spin quantum number later. An orbital is described by these three quantum numbers. I mean, the spin quantum number is not really describing an orbital. So this principal quantum number, angular momentum quantum number, and magnetic quantum number, these three quantum numbers, set of this three quantum number is actually referring to a specific atomic orbital. So a particle in a three-dimensional box has three quantum numbers, nx, ny, and nz. We have three quantum numbers to describe a particle in a three-dimensional box, in a three-dimensional system. Okay. And also for atomic orbital, we have three quantum numbers to describe one single orbital. That is not a coincidence. The world is three-dimensional, so quantum states naturally come with the three quantum numbers. The spin comes later, as I said already. So the reason why we have three quantum numbers to describe a single orbital, and that is because we are living in a three-dimensional world, as we have seen that for well, a cube, three-dimensional cube, three-dimensional box, we need also here the three different quantum numbers, x and y and z, to describe the energy. Okay, now you can see this equation. Okay. Later on, I'm going to also explain how we can derive this equation based on the Schrodinger's wave equation. But here, I would like to just shortly show you how we can come up to this equation based on the de Broglie equation and also the boundary condition. I already mentioned that the de Broglie equation looks like this. Okay. Okay. And then I also told you that according to the boundary condition of the one-dimensional box, the integer times half of the wavelength, okay, that should be the same as L, right? Also, we have to think about this, that the kinetic energy is the same as P square divided by 2m, okay? So we have three different relations. De Broglie equation, the relation that the multiple times of the half wavelength should be the same as the length of the particle L, and also the kinetic energy should be p squared divided by 2m. Okay. When you combine all the three, equation 1, equation 2, equation 3 together, then you can come up to this equation. Kinetic energy is n squared, so n squared, the integer square, Planck constant h square divided by 8ml square. Okay, so that is the energy equation the equation for the quantized energy levels for one-dimensional system. So if you extend this to three-dimensional system, then you have the same term for the x-axis, the same term for the y-axis, and for the same term you have for the z-axis. Okay, and then you can come up to this equation. So in one dimension, the kinetic energy of a particle in a box is proportional to the square of the integer, right? Square of the integer quantum number. In three dimensions, the total kinetic energy becomes the sum of three terms, one for the x direction, one for the y direction, one for the z direction, x, y, z. So the energy depends on nx square plus ny square plus nz square. So this is only true when Lx equals ny equals nz. So if the box would be a cube, then the energy of a particle with a mass of m should be proportional to nx square plus ny square plus nz square. So energy increases with the square of the quantum numbers. As the quantum number increases, the wavelength becomes shorter. But here is the key point. If the box is larger or the particle is heavier, uh, even increasing the quantum number does not raise the energy very much. The energy level becomes very closely spaced. So see denominators above. So see denominators here. So denominators, the mass and length of the particle L, m and L, they are all in the denominator part of the equation. So when m and L rather smaller, the energy gap should be larger. As the m and L becomes larger, the energy of a certain integer n, as well as the energy gap, becomes smaller and smaller. This energy gap becomes smaller. So if the box is large or the particle is heavy, when increasing the quantum number, even increasing the quantum number does not raise the energy very much. The energy levels become very closely spaced. Okay, electrons confined in atoms or molecules are light and trapped in a very small space or in very small spaces, so their energy jumps huge. Billiard balls are heavy and move in a huge space. Their energy levels are so close together that they look continuous. That's why electrons jump, billiard balls slide. Quantum effects are real. You just don't see them in everyday objects. So even for billiard balls, energy levels are quantized, but the energy gap is very small, so that the quantized energy levels are uh, uh, appear to be continuous. Okay, that doesn't mean that in the macroscopic world there is no quantum effect. There should be still some quantum effect, but only very, very small, so we don't see them. Okay, now same energy, different world degeneracy. So if the box is cube, all three sides are equal in length. And if an x cube plus ny cube plus nz cube is the same, then the energy is the same. So the state 111 has the lowest energy. 111. So when you write x and y and z within parentheses uh, as a representation of a set of three quantum numbers, then the 111 should be the lowest energy. Above that, there are three different states, 211, 121, 112. Each state has a wave propagating in a different direction, but the energy should be also the same. So in this case, we say degeneracy is 3. So 156, 165, 516, 561, 615, 651, 237, and so on and so forth. All these 12 sets of three quantum numbers, for each the sum of squares should become 62. You can try to calculate. So in every case, sum of the square of each should come up to 62. So for all the 12 states, uh, one can say that energy should be the same. So in this case, degeneracy is 12. What does higher degeneracy mean? So higher degeneracy means there are more states available at the same energy level. As the quantum numbers increase, degeneracy tends to increase as well. Okay, I think probably I'm going to stop at this point for today. So this is only this is the first lecture, so I try to explain a little bit slowly. And probably I may go a little bit faster from next time, but not that fast actually. Thank you for your attention.